I think we're about ready to get going here. I think we realized while we were sitting here talking that this says Go AI, but this is not a Go language AI. So if there's anybody who would like to change their minds, this is probably a good time. No? All right, that's great. Well, I'm Andrew Jackson, and seated here is Josh.
I'm Josh Hoak.
I'm a software engineer at Google. I work on intelligent devices. And
I'm also a software engineer at Google. I work on GKE, Kubernetes Engine.
Do you want to join me up here? It's probably going to work out a little better. That's right. Oh, it's blinding. All right, well, thank you for coming to our talk here about MiniGo, which is about making a Go AI using TensorFlow and Kubernetes. And our clicker is no longer clicking. That's cool.
Oh, is that working?
No, that's OK. All right, so for starters, what is MiniGo? MiniGo is an open source implementation of the AlphaZero algorithm described in a couple of papers by Deepmind. So if you've heard, can I get a quick show of hands? How many people have heard of AlphaGo, AlphaZero? All right, this is not AlphaGo. This is an implementation of AlphaGo from their papers, a ground-up open source rewrite that you can find at GitHub under the TensorFlow repository under MiniGo. And so that's what it is. What drove us to write MiniGo was because we're Go players. I've been a Go player for most of my adult life. I've worked as a volunteer for the American Go Association.
I played Go for 10 years. I made Go books. That's actually how I started programming. I made Python scripts that made Go books.
So we're both big Go players. And after the AlphaGo launch, debut, publication, whatever you want to call it, we figured there was still a lot to do here. And we really wanted to see some open source implementation of this algorithm and an open source version of this model that we could explore and learn with. And there's a lot of stuff there. So I'm not a machine learning expert, and neither is Josh.
I'm certainly not.
So MiniGo has been a good project for us to sort of learn this stuff, and it's also been an excellent way for us to get acquainted with all these things. TensorFlow kind of thought that this was a pretty good project as far as demonstrating how TensorFlow works, and the code is pretty small and approachable. So we hope that if you do decide to check this out and learn more about Go or learn more about machine learning and TensorFlow, that you find the code to be clean and easy to work with. So let's go back a little bit. What did we build MiniGo on top of? So the first paper, the first AlphaGo paper, Mastering the Game of Go with Deep Neural Networks and Tree Search, a friend of mine named Brian Lee wrote an implementation of that paper. He wrote sort of a skeleton implementation of it, just the policy outputs, and it was called MuGo. And you can see MuGo, since writing MuGo, Brian has gone on to work for Verily, which is another Alphabet company, else in Boston. But since he's a Go player, you know, I knew him as a Go player and was able to look at MuGo and say, well, this is a great clean implementation of the first paper. I can probably use that to build on the second paper, which described the AlphaZero algorithm. And really short, the difference between AlphaGo and AlphaZero is that AlphaZero had no human input. It basically started from random noise and was able to teach itself how to play Go. So you add those two things together, and we have MiniGo. This is, if you're like, why is that a robot falling off of a ladder? Don't worry, we will explain it. It'll all become clear. So
if you're a Go player,
the
ladder is symbolic.
Do we have any Go players out there who kind of?
Go players.
I see a couple of hands. So OK, so you might understand why there's a robot falling off a ladder. We'll get there, though. Everybody will get that in a second. So, so this is a great demonstration of using TensorFlow and Kubernetes. This is a 20% project that we started sort of in our spare time as Go players and enthusiasts. And one of the things that we needed to do was we had very few developer resources, by which I mean other enthusiast Go players who wanted to work on this project. And we really needed to sort of leverage our time and be able to spend our time writing code and not a lot of our time writing infrastructure, doing a lot of that build out. So that's sort of our motivation here. And to get to the point where we can start talking about how we used Kubernetes, I need to sort of explain what Go is and what machine learning is, because this is KubeCon and not a machine learning talk. So I'm going to try and do a very quick overview of Go and machine learning, and then turn it over to Josh to talk about how we use Kubernetes to build this reinforcement learning system. So what's Go? So 5 slides. Here's how the Go game starts. It's totally empty. And people take turns putting stones down on the board to sketch out territory. There's one rule, one very important rule, which is capturing, which is that a stone or a set of stones that are surrounded on all sides is then taken off the board, and that's a capture. You can capture multiple sets of stones. So you can see on the left those white stones. those strings of stones are connected orthogonally, and the new black stone that you see on the right side takes those stones off the board. I mentioned earlier that the goal is not to capture, the goal is to build territory. You can see here an example of a game where the two sides have sort of divided up the territory on the board. So unlike a game of chess where it starts with all the pieces and the pieces all go away, Go starts with an empty board and things are sort of built up. And the object your opponent, you're sort of trying to divide up the map into different parts of territory, and the person who has even just one more point is the winner. So it's a very different sort of game than the sort of maximalist games where the win conditions are very dire or bleak. You have to wipe out the enemy army or something like that. No, no, no. In Go, you just need to get a slightly better deal for yourself.
Yeah, and that's a good point. It's like a points game. And that's like, there aren't very many games like this where you're just trying to get points. And so it's a combination of territory here and captures in the previous diagram.
Pretty cool. So, and here's an example of MiniGo. We actually have, I hope that this GIF will reload. There we go. Perfect. So here's an example of how a game might unfold. Play starts in the corners.
So this is actually a MiniGo game.
This is actually MiniGo, right? Which is a little, So what you're seeing there, so the whole string of stones being taken off the board, that is a ladder. There's some interesting side effects of the AlphaZero algorithm, one of which is that this repeating pattern that is kind of obvious to humans is very difficult for the AlphaZero algorithm to learn. But it does learn them eventually. In the meantime, though, it falls for this trick that is a fairly easy one for humans to explain and avoid. For MiniGo, for whatever reason, that's beyond its ken.
And I should say this version of MiniGo is actually quite strong.
It's not bad.
This one is actually probably stronger than me, and I've been playing Go for 10 years. But you can see it's falling for the ladder.
It has this blind spot. Anyway, so we'll get more into that. But this is what a game of Go looks like. So that's Go in 5 slides. If you have more questions, please ask us afterward. Next, we're going to try and cover machine learning in 5 slides, and that's a little ambitious. But I should also preface this that I'm not a machine learning expert either. And this has been a project where I've learned a lot about it. So I hope that makes this explanation accessible. I would also encourage you guys, if you think this is interesting, please check out other resources. There's a lot that you can find. The short version is what is a neural network, or what is a machine learning algorithm? What is a model? What do we call these things? Basically, we have a pile of math that gives us an answer when we put in some data. That thing in the middle is the model. And in the case of a neural network, we have based that math on something that has biological inspiration. Like this structure in the middle is a bunch of linear combinations which are supposed to emulate neurons in the brain. They're not actually, and there's a lot of places where biologists go, hey, that's not how brains work. But that's what they're sort of supposed to simulate. And the important thing is to realize that this is a big pile of math. And the important thing about that math is that it's differentiable, kind of. And the other thing that's important to know is that it's really slow. So that's why folks are using GPUs and hardware accelerators to try and make that pile of math pretty fast. So that's an inference where we give it some data, we run it through the model, and we get out some answers. When we want to create that pile of math and make it any good, we want to train it. And what that means is that we want to quantify how bad that inference or that forward pass is. And we want to express that in a mathematical function called error or loss. And if you've ever done regressions, this is basically regression. You find some way to express the error of your prediction, and then you take the derivative of that, and you try to walk downhill. So once you can take the derivative of f, then you figure out how to change the stuff in the middle to make the error smaller. So that's training networks in a nutshell.
And I should say, just with a slight asterisk here, the thing that the image is like a perceptron or like a very simple neural network. But of course, for MiniGo, we're using a convolutional neural net. So we're kind of glossing over the entirety of convolutional neural nets.
All of that stuff, please go check it out somewhere else. But the important thing is that that's a lot of variables. That function of your error could be millions of variables. And taking the derivative of that is a real pain. But the important idea is that we want to essentially use that to revise and adjust all of the weights in our network to get a better model that's better able to give us the results that we want the next time. So how does MiniGo use these? So an inference for MiniGo means that we give it a board position and we get 2 values out. We want it to tell us what's the next move that's likely to be played and who's likely to win. What's the next move that's likely to be played is called the policy output. It is essentially an array of numbers where one number corresponds to each point, which is the probability of the move being played. And the second one, the who's ahead, who's going to win, that is the value output. And that's just a scalar between -1 and 1. With a 1 if black is going to win, and a -1 is white's going to win. That's all it is. So that's what our network spits out. What do we do with these numbers? What we do with these policy and value outputs is we do something called tree search. We do Monte Carlo tree search, which is a way of exploring the possible outcomes. We use the policy network not to assume that the most likely move will be played. We do a tree search and we try to figure out if it works, if it's a good move in this situation. So we use those policy outputs to sort of peer into the future and see what will happen if we play those moves. And as a result, that changes the policy. So the idea is that this tree search is an improvement on what the original policy outputs would provide. So the process is that playing a game using tree search produces a better game that we can use as input data to train the next version of our model. And this is kind of a pretty big idea. We can take this tree search that we do, and we can actually get our error function in this way. So we can define the error for that we will use to train our next version of our model as the difference between what the original policy output was and the move that was actually played, and the difference between what the value output was and the actual result of the game.
And just to recap, again, policy is?
Right, what move will be played next, and value is who's going to win the game. So when I say policy and value, I kind of say those interchangeable. That's right. A voice from the darkness here. You can come into the light. It's totally fine. All right, so that's sort of, this is our 5-slide machine learning summary, which I hope is, we're just sort of treating it all as a black box. There's a whole lot of other stuff that goes in there that I'm not super clear on myself, but when you use great libraries like TensorFlow and abstractions, you don't necessarily need to worry exactly about how all of these things happen. But a model is a big pile of math we use to give us answers. We measure the error, comparing those answers with the answers that we know or think we know. We train the model to minimize that error. MiniGo's model outputs this policy and value. We use those in tree search to play games, and then we use those games to become better, in theory, if everything's working right. And so that is what we call a reinforcement learning loop, where self-play produces the new data that we use, and then training produces the next model that we use. And if that happens, then you have this very virtuous reinforcing cycle. There's a whole bunch of other details on why these are sometimes hard to set up and why it was so hard for folks to arrive at this very clever algorithm. But that's all stuff that I'm sure there are some better qualified people to give those talks. In any event, the important takeaway here is that self-play, that tree search, the process of creating data for the next version of your model is incredibly computationally expensive. We need to produce each move that we decide to make in a self-play game requires thousands of inferences, thousands of forward passes of the model. And we do that hundreds of times per game to play a single game. And then we need tens of thousands of games before we can train a new model. So as a result, this is the huge parallelizable part of the problem, where once I had implemented the algorithm described in the paper, once I had some tests to make sure that was working, I said to myself, oh my gosh, I need to play millions of games, and playing a game takes a surprisingly long amount of time. So that kind of keys up the problem, and I'm sure that you guys all kind of know where I'm going with this and what I used to do this, is this was me thinking to myself, how am I going to do this? I said, well, I could manage a whole bunch of VMs with a soup of bash scripts.
Which is great.
No, that would have been terrible. That would have been awful. I had all of these problems, and I went to see my friend who's on the Kubernetes team. I said, how can I do this? How am I going to do this? Should I use containers for this? What's the problem? Should I make a giant work queue? Should I do some big stateful app that would pass out work? What's the right way for me to do this? And I think, so I went to go see Josh. And what did you like laugh at me first?
I said big pile of bash scripts.
Big pile of bash scripts. That's exactly what you said. All right, so take it away.
OK, so to recap, where are we at this point? Well, we've got a Python program that uses TensorFlow and runs locally. That's where we are right now. So what happens next? OK, so the first thing we did was, OK, we got to stop storing our games on the local file system. So we're like, OK, well, how about Google Cloud Storage? Well, we're at Google, right? So we're going to use GCS. So we're going to store all our SGFs. So I'm going to use SGF sometimes. That's Go speak for Go file.
A game file.
A game file.
It's a game file.
And we're going to store all our game files in Google Cloud Storage, and we're going to store all our models in Google Cloud Storage. This is going to be really simple. We're going to push SGFs up. We're going to read them down, use them to train, push the new model up, and so on and so on.
This was a pretty contained binary. It would do one thing. It would you would call it, and it would play a game, and it would write out the data, and then it would shut down.
OK, but we're still not. It's still running locally. OK, so what about next? OK, well let's containerize it. Let's put it in a Docker image. OK, so super simple. We'll put in a Docker image, run it on GCE. Great. Well, I should say, this turns out to be actually where all our trouble comes in. So the hardest part for us has been putting in a Docker image. I should say TensorFlow.
Some of it.
Some of it.
Most of it.
Some of it.
Yeah.
To really get a good performance out of TensorFlow for CPUs, for example, we compile with special flags to really get good optimization.
Yeah. There's sort of this tension, right, where containers give you the idea that you don't need to worry about the machine that they're on, really. But TensorFlow and requiring GPUs makes you actually sort of be concerned about the architecture, like the processor architecture that you're running on.
And we'll talk a little bit about NVIDIA libraries in a little bit.
Oh yeah, NVIDIA libraries. Great.
So here's where we are. But what are we going to parallelize, and where does Kubernetes come in? And of course, here's where it comes in. So we've got this self-play cycle, and to recall, how many games are we going to be producing? It's around 20,000 games every time we want to train. So that's our batch size. And again, we need millions of games. So embarrassingly parallelizable. So what are we going to do next? And so I asked my team, and I was like, hey, what do you think? And one of my team members, Jacob Beecham, was like, hey, how about you use a Kubernetes job?
Right.
Awesome. So created Kubernetes job. We're going to crank up the parallelism to 20,000, run a bunch of VMs, go. And it keeps running and running and running and running and running and running. And it turns out it's producing 30,000, 40,000. I'm like, oh my gosh, what is happening?
This was pretty funny. I just specified desired completions. I said 20,000, and surely it will reach that number, but it doesn't actually. After 1,000, it would reach 1,000, and it would just stop there. And I was very confused.
So turns out this is a funny caveat of the way the batch API currently works, is that Daniel's shaking his head and cringing. So currently it checks the number of finished jobs by looking at etcd to see how many things are in etcd have finished. Right. But in GKE, for scalability, we set that number pretty low so that we don't have masters that die.
Because it's keeping track of all of the things associated with
Exactly. We don't want to have extra XCG junk.
This actually turned out great. Like this little wrinkle in the API actually was just what we wanted to do, because we could basically specify an absurdly high number of desired completions.
And it runs forever.
And it would run forever. And we just restructured the job that each time it started up, it would pull down the latest model. So as a result, there was this enormous cluster of self-play workers, which are essentially waking up, playing a game with the latest model, writing out the data, and shutting back to sleep. And as soon as I push a new model to GCS, there's no half-finished files, there's no contention. If anything goes wrong with any of these jobs, they just shut down and start over again. So
it's great.
Worked great.
So OK, but we're still running on CPUs, and we got to speed this up.
Right.
So next, we started running with GPUs. And again, there's the Docker images, right? So we started doing this way back in January when they first produced their paper.
December. I think the paper came out last year in November.
So something like that. Anyway, but in any case, the Alpha API in Kubernetes and GKE was just getting going around this time. And we were like, great, we're going to use it. We're going to use NVIDIA GPUs. And of course, we were like, well, how do we stick the CUDA libraries and the NVIDIA libraries
and drivers and all of
that?
Yeah,
anyway, so it took some work, but we got it working, and wow.
Yeah,
so
they're way faster.
So
it's really
on CPUs, we were getting 7 readouts a second. So that means every readout is an inference, right? So like one run through of the neural net, we were getting 250 readouts a second using just a K80.
Which is a few generations back.
Yeah, it's not even the latest NVIDIA GPU.
It was K80s, P100s, and now V100s.
V100s, that's right.
There's still some...
this was fantastic. So now we were able to train self-play much faster.
Right.
So now we're really cranking out games, and we're really training our model.
That's right. So we should go back just a second here, which is that this graph about GPUs, it's the same graph. Like the huge advantage here was that we didn't have to really change our pipeline. We just changed our Docker image, and we had this huge performance increase. Like, I'm sure that I'm preaching to the choir here. You guys all know that this is the great advantage. But to me, as an application developer who's like, do I really want to use containers? Aren't they going to make it hard for me to get all the performance out of them? No, they didn't. There wasn't any sort of performance that was hidden by the Docker runtime or by Kubernetes. And as a result, I didn't have to change any code. I just had to change the Docker image. It was a huge success for me personally, and I was really dreading it. And I should also point out that the whole driver situation has gotten a lot better just in the last 4 months.
So at this point, so if you're interested more in GPUs, Rohit, who's on the GKE, the Kubernetes team at Google, is going to give a talk tomorrow. It's going to go into more detail. But in GKE, we've now a beta API for GPUs. And now NVIDIA is providing the CUDA libraries directly in the image. So it's great. OK, so I'm going to want to get to the demo, because we're going to have a MiniGo demo. But I just want to mention one more thing. So have you ever played Factorio and you're like putting together parts of your factory, right? So this is kind of the Factorio process. We had our self-play pipeline, but now what we wanted to know if MiniGo is getting better. And how do you test that? You have MiniGo play MiniGo, but not just the same model anymore. You have MiniGo playing
different models,
a whole bunch of different MiniGos.
We had a whole set of checkpoints in sort of a zoo of models. And we wanted to be able to track how much better the new models were getting by having them play against all of the older versions, against different sets.
And we didn't do this, but in theory, you could like play against like other Go playing AIs.
That's right. We had that as well. There's a number of open source engines.
We haven't done that yet. So. That's definitely something we'd like to do.
Yeah.
OK, so this is the cool part. We're going to show MiniGo. So we're going to show actually MiniGUI. And I should say, you can do this too. All of our data is open source. It's on GCS. And I'm just going to basically do exactly what's here. So I should say, this uses a Docker image. Docker image is about 1 gig. Don't all do it, because you might kill everything. So let's go over to terminal.
You mean like the Wi-Fi?
Yeah, like don't kill. That would be really sad.
That would be.
OK, so board size. Can everybody see that? It doesn't really matter. We're going to get out of this pretty quick. OK, so I've set the board size. I've set the model. And
it's a little bash script which fetches the image.
We've kicked off our Docker container for MiniGUI.
Right.
We've pulled down the model. I've actually pre-pulled it. And let's go back to Chrome. Boom.
Nope, no Chrome.
No Chrome.
No, we didn't get Chrome back. Maybe just turn off full screen for the terminal. There we go. Come back. Come back.
How do I navigate between? OK.
Hard problems in computer science.
OK. There we go.
Right.
All right.
Here it is.
Readouts. 2000.
It's not. You don't have the cursor yet.
All right.
You might say this looks like a smaller board than the normal Go boards. That's right. This is a local version running right off of the laptop here. So we don't have.
That's right. So this is CPUs. So it's going to be much slower, which is actually good. So you can actually like see it do things.
This is a much smaller model.
And there it goes. So now MiniGo is playing MiniGo. And I should say something. You can't train like a 19 by 19 model and expect it to play 9 by 9. So this is a previous version where we trained it on 9 by 9s.
A different model.
A different model. And so just a brief, what's going on here?
Let's pause it.
Let's pause it.
Really fast.
All right. So on the left, we have what's called the principal variation, which is the variation that MiniGo thinks is the most likely variation, right? On the top, in the sort of top middle column, that is the exploration. It's actually a sample of all the things that MiniGo is trying, right? So you can see that after trying a whole bunch of things, it's discovered better variations. But the first move, it's pretty confident about that first move. And you can see that actually in the middle diagram, which is the heat map. That is, where does MiniGo think it's going to play next, right? So that is actually, going back to the policy value net thing, that's the output of the policy network. And then the final thing is this is the value network. This is, if I play here, how do I change the score of the game, right? So basically, you can see that like it's flipping white and black and white and black. So it's from the perspective of the current player. Am I going to like make the game worse or better? So now like white White's not doing quite as good. Oh, black is coming back.
Actually, it looks like it's going to be a big co-fight. You can see the graph in the upper right-hand corner is its graph of who it thinks is winning.
That's right.
So as it goes up, it thinks black is going to win. As it goes down, it thinks white's going to win. So right now, it's back to about 50%, which means it thinks it could be anyone's game. So,
anyone's game.
This is a pretty fun tool that we use to sort of inspect, what it's thinking about, what's happening. It's pretty cool to be able to sort of peer inside what it's looking at.
Yeah, I should say you can do this too. It's totally open source, totally available.
Right.
And in theory, so this is, if you know, okay, so this is a little more technical. If you know about how to run Go AIs, this is using GTP. You can plug in any other Go AI into this.
GTP is the Go text protocol. I think it dates back to the 80s and GNU-Go. And it's basically running all of this over standard out and standard error. And if you guys are like, that sounds strange.
Awesome.
Well, yeah, awesome. That's maybe not the first word I'd use. We're actually piping standard out and standard error over WebSockets, and then the JavaScript is rendering all this on the front end, which
is awesome.
It's a little interesting, but it gives us compatibility with all of the other Go engines as well. So it's pretty interesting stuff.
All right. So that is, I know this is my favorite thing, but we're gonna switch. We're gonna wrap it up. Cool. Switch over to slides.
There's our slide.
There we go.
Yeah, that's right. It would be a great screensaver, except it would also generate a lot of heat because it's doing a lot of work. It's a great way to make your battery
Where do I present? Oh, it's this thing. There we go. And cool.
So that's about it. Again, we've done this all as sort of public domain stuff. All of the data, all of the models, all of our code is all on GitHub. Well, the data and the models are all on
GCS.
GCS, cloud storage.
Yep.
And that's all available. Again, this has sort of been a labor of love by a number of interested Go players.
Yeah,
so
MiniGUI was written by another volunteer.
Yeah.
CloudyGo was, which I didn't show, is written by another volunteer.
Yeah, this is front end into all this data that we're producing. It's a lot of fun. We've had a great time doing it. This is also very timely. I don't know if you guys know, but just last night, Facebook announced their open source Go AI. Which was
awesome.
Just released. It's really exciting, honestly.
I think
it's
super exciting.
We're hoping that this is sort of the way forward for AI research, that these things will happen with code attached, with with
compatibility, and so we can all kind of work together. Right?
Yeah,
exactly.
It's pretty exciting stuff. I'm really looking forward to digging into their code once the talk's over. So.
Right.
Yeah, exactly. I just found out.
It's trying to not look at. Okay, we're gonna work on this talk. Okay.
Anyway, so I think that's what we had. Do we have any questions? Is there anything?
I want to just say a couple more things. There were a couple things that we didn't make into the talk that we really, really want to still do.
Right.
TPUs just came out right before we were working on all this. Didn't quite make it into the talk. Integration with KubeFlow is still something we really, really want. And of course, Argo, which I don't know how much you know, but it's this awesome execution workflow engine. So definitely things we still want to make for MiniGo. Right. Definitely a lot of work to do.
For sure.
Yeah,
which has been a lot of fun. So thanks, everyone. Do we have any questions?
Question.
All
right.
Want
to go for it?
Yeah. Where was that question? I didn't see your hand.
Oh, it's.
I have to get you the microphone.
So as you said, playing 20,000 games of Go simultaneously is embarrassingly parallel. And I was wondering if you thought about how this might apply to problems that aren't as embarrassingly parallel, where you need some communication between the different copies that are running simultaneously.
There's definitely a lot of ways in which the AlphaGo Zero approach is nice and contained in a test bed. It's one of the reasons that we built it the way that we did was because the data pipeline had the requirements it did. I think that if we did not have quite as an embarrassingly parallel a problem, we might have picked a different way of structuring it. Like we probably wouldn't have used the batch API and probably would have had to push a lot more of that logic into the application layer. But because this is a problem with that sort of parallelism, we were able to do the simplest thing that could work, which was basically using GCS as a big file system. So it's a great question, but I think the importance is to try and sort of fit the solution to the problem domain, right? And in my case in particular, since there's so very few software developers that were working on this, it was really a matter of how can I do the most with the least amount of developer time. the scarce resource was really developer time, which is what I was trying to maximize for. So, more questions? Did I see a hand? No? Yeah? Have one? I'm going to get a good workout jogging around.
Hey, so 2 things. First, if you want to integrate the KubeFlow, that would make a great addition to KubeFlow example. So if you're game, I'm game. I'm be happy to help you with that. And the second one, have you tried distributed TensorFlow? Because I assume that your distribution is one job per play, but the job itself is not distributed, and
Those are great questions, actually. To speak to the second one first.
Go ahead.
We're always looking, where is our bottleneck? Where is our bottleneck? Where is our bottleneck? For the long time, it was self-play. But we're actually working on a C++ rewrite, and it's going to be even faster. Not hugely faster, because most of our bottleneck has been
3 times faster.
3 times faster.
3 times faster.
Okay,
yeah.
it's 3 times faster.
Yeah. Wow.
But
because we're able to saturate the GPUs better. There's some
all right. So at that point, then yes, then we really have to change the way training works, and then distributed TensorFlow
is fantastic when you need to shard your training job. But for us, the bottleneck has always been the data creation,
that's going to change real quick.
Which is going to change pretty soon. So basically, as soon as we get back, and I'd love to do that. Let's talk. Okay. Another question? Any other questions? I think we might be almost out of time. Yep.
The relationship with TensorFlow and the way Go affected its popularity, as an example, which came first? The developer interest in TensorFlow and that dragged interest in the Go challenge, or did the Go challenge really drive the community of TensorFlow?
That is a great question. First, I kind of have to take the easy one, which is that Go came first, because Go is several thousand years old, so obviously Go came first. But the question of TensorFlow, did interest in Go drive TensorFlow adoption? The specifics of the architecture underneath AlphaGo is that it is a convolutional neural network, which is very similar to ResNet and the other image classifiers that people have been working on.
In fact, we treat Go as an image.
Basically, like it's a picture recognition
net.
problem. Yeah, the convolutional net basically treats it like a grayscale image and is able to extract features from that in the same way that a lot of the same object recognition algorithms work. So it's more of a repurposing of some very effective ways to train image classifiers have been used in the game of Go. And arriving at that particular architecture as described in the paper is where a lot of the hard research work was done. For us now, this was about a software engineering challenge and scaling challenge.
But TensorFlow is perfectly suited to it.
Right.
It's fantastic for convolutional neural nets.
Right. So it's a great question. Did that answer kind of where you're going with that?
Without the Go challenge, would TensorFlow have really taken off in terms of viral adoption?
Without the Go challenge, would TensorFlow taken off?
Yeah, TensorFlow is awesome.
I think that ResNet and the image classifiers used by Google have really been driving a lot of the TensorFlow, in particular this interest in training these really big models. All right, I think we're out of time. If anybody has any other questions for us, we'll be outside.
Cool.
Thanks, everyone.
Thank you.